All right. Second video in the series here. I'm going to try this. I tried it once, didn't work very well. But we're talking about solids of revolution. So I want to get an idea of what solids of revolution look like. And so I went around the house and I found some things. This is an example of a solid of revolution. And the important characteristic is that all the cross sections are circles. So it's made up of a bunch. This would be an example of naturally disk method. These are pretty thick disks, but you can see that you can build this whole shape by basically gluing these disks together along a central axis. And if we could come up with an equation for this bumpy edge down the side here, then we could use calculus to come up with the volume of this particular shape. Okay, so that is one example. I also found, let's see, this candlestick. Okay, same basic idea. There's a central axis. The end is a circle. Every cross section would be a circle. I kind of marked a radius on this particular one. And you could build this whole thing if it was sliced up. You can see that the slices are a little bit thinner on this one that you have to do to capture all of these shapes, but this is an example of a solid of revolution. I did knocked over my stack here now, but I'll pick them back up. This is a approximation of a cylinder. Okay, in fact, this is just a stack of quarters here. I've marked the top quarter with a radius on there, and so I could find the volume of the stack of the quarters basically by figuring out what the volume of one quarter was, right, and then multiplying by the height in some form of that to come up with an overall volume of that. Okay. We also have, this is, if you were unfamiliar with what a washer is, this is a washer. This is why it's called the washer method, because that method tends to leave a hole in the middle. The important things to keep track of are there is an overall outer radius on this thing, and then there is a little small inside radius of that. And we'll take a look at that a little bit more and how that works. But you can, in certain circumstances, you may have multiple washer-looking things. This is a really rough approximation of a cone. That just happened to be the only size washers that I had. We can approximate that cone a little bit slightly better. I was not, arts and crafts are not my thing. But this is my cardboard approximation of a cone. You can see the slope. It's a truncated cone. The top's been cut off of this. But we can see how we can build that cone by stacking together discs. Here's my top disc. My top disc has a particular radius. And what makes every disc different is everyone's got a little bit bigger radius than the one before. But they all have a thickness. I did this out of cardboard, so we'd have a little bit of thickness on there. And so because this has thickness and two dimensions otherwise, this has a volume. And finding the volume of that one thing and then using calculus maybe to find the volumes of all the other ones and add them together, that's the application that we're doing right here. And discs and washers are the ones that you've already done. I have a couple of representations of the shell method, which Khan Academy didn't do for us, but this will be my first example. There is a volume of tape that is on this roll of tape. And one way to find that volume, I mean, we could try to slice it this way, but it's not naturally that way. The reason this has some volume is because this tape, I can take off a layer of it. If I go back, I kind of marked my starting point there. And if I tear that off at that point, then I have this strip of tape, which was the outside layer on that. And that strip of tape has a very little bit of thickness, right? You can see the thickness that's there. And it has a length and a width, this length that goes along this way, which is 2 times pi times the radius from which I took it. So from the center here out to where that layer was, that was a particular radius, and it was one trip around there, which is the circumference. So it's circumference long, and it has a thickness or a width. We'll call this here, or I'll call it a height that way. And then it has a thickness that is very small. That's what we would call a D something. So it's like the little bit of volume that's represented by this is 2 times pi times the radius times the height, that's the area of this rectangle, times however thick it is. And that's where the calculus starts to come in on the shell method. My other arts and crafts method for the shell, I'm going to take my tape off of this and just try to hold it together. Here is my cone represented with the shell method. And so on its outer layer here, I can pull that outer layer off and I get a rectangle. And the next layer on there is also a rectangle. And my next layer is a rectangle, and I can see every rectangle in this case is a little bit taller than the one before, but not quite as long. There's my formula for the area of that one again. This one happened to be at a different, if I look on this, my radius as I work from the inside out there would determine that since this one was closer to the axis, its radius was smaller, and so it's not quite as long. So obviously it's a pretty rough estimate of a cone, but I didn't want to cut out that much cardboard. But each one of these is supposed to represent one layer of that on there, and we can see that we could really smooth this cone out if we made much thinner slices of everything along the way. So that's the picture of the shell method and how it builds up a volume instead of stacking discs or washers together. It layers on like a roll of tape or a roll of toilet paper or paper towels or something like that. Okay. So this is an example of where I might end up with washers, and I've kind of labeled this one already here. We can see this was a shape that we had looked at in the last video with a sample slice on here. And when that sample slice, in this case, I'm rotating around the x-axis. So the way that you slice and how that slice is related to the axis you rotate around is going to determine what shapes you're getting. So since this slice is not directly connected to the axis, but it's perpendicular to the axis, when I spin that slice back into the page and out of the page and around this axis, it's going to create a washer. And so the volume of that washer is the big radius, the pi times the big radius squared. That would give me a disk, but I need to subtract out the hollow piece in the middle, so minus pi times the little radius squared times its thickness dx, which it has because of the way that I sliced this one. Okay, and so that combination will make a washer. We need to get these variables to agree in here, but that's for the next video. Okay, so what creates cylindrical shells? My cylindrical shell is going to come from this picture. Okay, I have the same thing. I've sliced the same way, but now this time I am going to rotate around the y-axis. And when I spin this vertical piece around the y-axis, then it's going to create just a single layer of this shape. We'll take a look in a minute here of what that shape's going to end up looking like. And so this is that would lay out into a rectangle just like this strip of tape down here that is 2 times pi times r long. It has height represented by a difference between the y values of these two functions. So the top y value minus the bottom y value, that's a bigger number minus a smaller, should give me a positive number. And it also has a thickness of dx. And so what's happened here is my slice is now parallel instead of perpendicular to the axis that I'm rotating around. And so that creates shells perpendicular to each other, and you tend to get discs and washers. Okay. Now, let me see if I can get this on the horizontal axis. Okay, this is set up in 3 dimensions here. So I'm going to just slide this thing along here. I'm going to try to slide that thing along there. And then we'll see if we can zoom in because it's zoomed out quite a ways on this. Come on, search form the solid. If I can get it to working really well earlier. Why it doesn't. There we go. Okay, so you can kind of see if it got all the way around there. Now it's jump all over the place on me. I didn't quite get it all the way around, but as I move it around here, it kind of looks like a bowl with a cone shape on the inside of that bowl. And so that's what it looks like if we were to form this thing by making washers and putting it together. If I rotate it instead around a vertical line, this one, see if I can get that to adjust in here and let us see what that looks like. And hopefully it'll let me spin that axis around to get a look at it so that we can see, well, there it is, kind of upside down. Let's see if we can get it right side up. It's a little bit backwards there, but you can see it almost takes on a diamond shape, even though it's curved up here and then has that gap in the middle. So it is definitely a little bit different shape that I get that direction. All right. And that is as much as I want to try to do with this video right now, but hopefully actually worked this time.